Okay. Okay. Thanks everybody for attending this edition of DVClub. It's a pleasure to have all of you here. We haven't seen such a big turnout before, so it's really heartening to see such a good turnout for DVClub. This is the fourth edition of DVClub that we have hosted in the past 10 months. We have had DVClubs on different topics. The first topic was formal verification, which we had in around September timeframe last year. We had one on UVM subsequently, and we had one DVClub in performance modeling in November last year. So this is the first DVClub edition in 2015, and I believe many of you will find the topics that we are going to be discussed today very interesting. I'll just give a quick summary of who the presenters are today. Our first presenter is Surinder from Samsung. He'll be presenting online. He's in Delhi currently. His topic is about simulation acceleration on PXP. Surinder's presentation will run for around half an hour to 5 minutes. After that, we'll have the second presenter from Cadence. The presenter from Cadence is Sandeep Gore. I think he's on the way. He should be here in 5 minutes. We'll have a 15-minute break after that. And we'll have the final presentation by Chris Das from Test and Verification Solutions 4. We'll have refreshments after all the presentations are over. This is an informal event, so please feel free to ask questions. You can raise your hands if the presenter is presenting it live. If the presenter is virtual, then we can have around questions after the presentation is complete. To start with, let me introduce Surinder. Surinder is working as a chief engineer with Samsung Electronics currently, and he is employed simulation acceleration in a couple of projects. He has more than 10 years of experience in the VLSI industry, and he has worked on various verification methodologies for a range of different projects. Topic of his presentation today is simulation acceleration on PXP. As per Surinder, in order to meet the time to market constraints and perform complex verification at different levels, simulation acceleration is a must in today's verification environment. Surinder will start by explaining the benefits of simulation acceleration, and he'll highlight one example on how to profile the TB on Palladium. The key points that Surinder's presentation will cover today are the benefits of simulation acceleration, test bench profiling, and reusability. I'll hand it to Surinder. Thank you.
Hello? Hello? Am I audible?
We can. Yeah, you're audible. You can start, please.
Okay. Hello, morning all. So this is Surinder Sood, and I have been invited to present a session on simulation acceleration. So I will start right away. So agenda which I'll be covering is the simulation versus acceleration. So why do we need acceleration? What is the scope of simulation acceleration? And what challenges we face while doing the hardware assisted verification, also called as simulation acceleration. So till now today the trends in verification have varied a lot. So some 10 years back we started with the conventional verification, in which we use the Verilog and the DAC stuff. And later on, the various verification methodologies came, like EVC, then VMM, then OVM, and now UVM. So as the verification enhancements keep on going, so was the design complexity. So designs, they kept on getting more and more complex in terms of gate count, in terms of functionality over all area. And since complexity of SOCs also increased, so challenge to verify that functionality in the stipulated thing, which is strict in some sense, was also enhanced. So as the evolution processes, we are here with a new approach, with a new idea which we call as simulation acceleration. So as the design complexity increases, so the time taken to execute a particular test, it also increases with time. So this means that the legacy simulation methodologies, they are not sufficient enough to verify a particular design within a stipulated time. So that is why a new idea of simulation acceleration has come into picture. So what does it mean and why do we need it? Let's start right away. So as I said, that SDL simulation takes a lot of time. So with increasing design complexity, time required to run a particular test also increases. So time to market also gets affected because of this, because we are not able to finish verification within strict time schedules. So moreover, we want to verify beyond verification. We want to see how the design behaves during the verification course itself, when it is integrated with other modules like software modules or form modules. And all those things cannot be realized when we are doing the SOC verification in a short span of time. And moreover, we also want to do prototyping and the verification stuff. So we also want to do hardware software co-verification along with the verification stuff within a given time span. So with just the SOC simulation perspective, all these things are not possible. And we require more time if we want to test all these things before actual time to market arrives. So the solution is simulation acceleration. So when we compare simulation with acceleration, and if we try to reason out why acceleration is better as compared to simulation, so there are various reasons to it. The primary reason being definitely the time. So when we are running the simulation, it takes hours to complete a single test on SOC. I have seen this in my various projects while working for x86 verification. So one test on an average is to take around 2 hours to complete. You think of duration which employs say 1,000 tests, so it will definitely takes weeks time or more than that to complete. But when we employ the same stuff using acceleration, so within an I wink I can say your one test can complete. So definitely if we are able to save time, then time to market can be safeguarded. During the course of verification, when we are finding some issues in the design and we want to debug the design, so the debugging is very tough when we are doing it simulation SOC level. With acceleration, debugging is easy in the sense like we can dump the requisite stuff in small span of time and we can start debugging. So, and third thing is definitely compilation, so which is quite fast when we do it on acceleration as compared to simulation stuff. So since these 2-3 points are prominent, as a consequence of which the productivity it's quite less as compared to acceleration based verification. And finally, it's amount of memory which is required in case of simulation. If it grows in size, the spool will start sinking. So, but when we do acceleration based verification, so enough memory is available for on the emulators itself, and emulators are quite fast, despite the fact that if memory increases, they are not that inefficient. So, what is acceleration environment? So, what does it consist of, and how do you do it? Let's move ahead in that regard. So, acceleration environment is just similar to simulation based environment. We are having a existing test bench, a UBC or whatever it is, UBC systems or any DVC environment. So existing test bench, we are actually integrating it with the design. So design is sitting on our Palladium or any emulator which is available in the market. And so this means that whatever the simulation environment we coded for, so that that can be reused in the acceleration environment. So in the sense that we are accelerating the simulation by interacting it with the Palladium or an emulator in which the design sits. And the communication interface between the test bench and the design is a high-speed interface. So so it depends upon the requirements what type of high-speed interface we can have, speed bridges or PCI speed bridges or a standard skin pipe interface will be sufficed. So such type of environment, it allows us system level debugging easiness, and it is ideal for any type of verification activity, let it be block level, chip level, or SoC level validation. And we are reusing the simulation like environment, so definitely the overhead to develop acceleratable environment is less. So moving ahead, as I told that a simulation acceleration environment consists of a UVC. So UVC typically consists of an agent, sequencer, driver, monitor, and all that stuff. And when we interface this UVC with our Palladium or any emulator, we require a high-speed connection. So high-speed connection typically at IP level we are normally using the skinny pipes. So in this case, the driver which was a part of UVC becomes a proxy driver because it stimulates the traffic, and then we send the traffic across a scheme and send it to a second part of the driver which is sitting on the Palladium, and it is called a BFM. So using BFM we stimulate the DUT, and this BFM is actually a mechanism to send or receive the stuff between hardware and software. So now what is the scope of the simulation acceleration? In simulation acceleration, the test runs very fast. Using simulation acceleration, various environment we can profile it. So we can profile our existing UVC so that it runs much faster when it is as compared to when it is running on the SDL simulation environment. And using performance of the performance profiling of our environment, so so DUT execution can be improved, and using simulation acceleration, time to market can be safeguarded. So because now we are running fast, using simulation acceleration, so we can prototype our design along with the verification. So this means that from scope point of view, so it has a lot of scope when it is compared with the normal simulation stuff. So but while doing so, there are subtle challenges which we need to address when we move to the hardware level from the software level. So the challenges are follows. The speed of the SDL simulation is primary bottleneck of the design cycle when it comes to verification of ever-growing SDL designs. Limiting the number of simulation tests to meet the requirements of tight schedules is alarming and raises doubt about the completeness of the verification. Newer methodologies like UVM or VMM automate the verification process with the constrained random test generators but require much longer simulation times. So the remedy for ever-increasing simulation time is using emulation techniques for simulation acceleration. So this means that as we are randomizing a particular test, so as we are adding more stimulus to a particular test, so the time to run the test is sacrificed. So in order to safeguard that, we need to move to the emulation based simulation. So and to address this challenge, so we have to do the performance maximization. So there are various ways of doing the performance maximization. So one is by using IES profiler on a standalone UVC or any standard test bench environment, and then provide a speed up estimate when the test will be run on the emulator. So when we run a IES profiler on a standard UVC based environment, so it provides us with the subtle data. So the data is provided as follows. It gives us a time, percentage of time spent in DUT execution. It also gives the time spent when your software environment or the UVC environment is executed. Time spent in the software simulation time. So all these details are provided by the profiler, using which we can actually calculate the estimate average case speed up which can be obtained. So it is nothing but a ratio of software simulation runtime with a cosim runtime, and we can get some X factor which we have to concentrate upon in order to optimize my UVC based environment. So once I'm able to attack to this X factor and then integrate my UVC environment with the Palladium, So definitely that environment will be running faster, better, and more efficient. So once this is done, and the next step comes when we do profiling onto the hardware which sits on the Palladium. So when we so in that case we enable the IES profiler to do the hardware optimization as well. So when we do that hardware optimization, then we can further profile our environment so that tests run faster, tests run more efficiently, and more design areas are explored from by our verification environment. So when we enable the hardware profiler using the same IES mechanism, so we make use of a utility called IXCOM. So it provides this type of information. So the category wise, like we are having behavioral evaluation statistics. So it tells the how much is the total number of behavioral evaluations which are done per module. So in the hardware. So then hardware definitely interacts with the test bench environment. So the test bench environment has various type of interaction mechanisms like DPA calls, SVS sessions, system tasks, so or various pipe-based communication interfaces. So second type of information which we get once we enable the hardware profiler, so is the total number of such calls which have happened during a given run, along with the line and file information for these calls. It also reports the time for the DPA calls, including the time taken in passing parameters from software to hardware. Third category of details it reports is the event statistics with regard to inputs and outputs at the interface level. So these are also important from synchronization perspective between hardware and software. So the focus should be to have as less event statistics as possible so that there are less synchronization events to be triggered upon. Force release statistics, another category. It reports the number of force release operations on the duty signals during the hardware run. Then finally, if we are having any memory, then what are the read and write statistics with regard to the memory we are playing with. So that is also one overhead while doing the hardware software profiling. So we have to take into consideration all these software as well as hardware profiler logs while doing the optimization. And this is the biggest challenge when we are doing the hardware software verification. So this is just a snippet of the log. So when we run, hardware profiling. So the first information it gives us the maximum hardware operating speed, that is the clock frequency in case of PXP. Then what type of clocking mode we are working with. How many hardware evaluations are done, as I show in the previous table. Then it also gives the acceleration speed achieved, which is in this case as an example is 235 kilohertz. And how much is the total number of hardware synchronizations executed. So and then XC profile it has generated, which tells what is the percentage of time hardware was being evaluated, what were the software simulation percentage time, and what were the synchronization overheads. So using this information, so we have to profile our hardware software environment. So the analysis in this context is the synchronization. If you see the synchronization figure, it is quite huge, and it has happened because of the slow clock. So if you see the previous log, so if you see the input event statistics, so it is showing that 821190, these are the total number of synchronizations which were to be happen with regard to the slow clock. So so this is an overhead in this case, and because of which we were not able to achieve much acceleration, and because of this again only 55% of the time was spent on the hardware. So using these values, so we can have a generic calculation, so which will tell us like what is the total time spent in the hardware software synchronization. So that is nothing but a channel latency into hardware software synchronization. So this is 6.92 seconds. Then time spent on the hardware emulation, which we already know, and finally from this we can calculate what is the total time spent in executing the DUT alone, which is quite less, and it's 2.69 seconds. So from this example we see that that the major bottleneck in this case, or the major time which is consumed, is 6.92 seconds, which is for the category hardware software synchronizations. If we can optimize this time, then our test will run further faster, and the total amount of time to be spent for the DUT will get a good proportion with regard to the total time. So this means that we can simply say that the main bottleneck for this environment is number of hardware-software synchronizations. And to improve the performance between the DUT and TV communication, we must use some piped communication interface so that the synchronizations are reduced to as much less as possible. And moreover, we must use the clocks which are generated from the DUT itself. Rather than TV sending the clock, DUT generates faster clock, and the entire Palladium should work, entire design sitting on the Palladium should work on that clock. So this is how, once we enable profiling for software, for hardware, we can regress and optimize our environment to achieve the maximum performance. So other ways of performance tuning can be like we can based on the IXCOM profiler, we can move the major portion of the test bench to the Palladium. So this may include, let us say you want to move collector code to the PXP, or you want to move the data generation from TV to PXP, or for some tests you want to pre-generate the traffic data. Once we preload the stuff, once we preload the our design with initial stimulus, then time is saved to run the test and to execute it fully. And memory accesses we can do from the back door if there are more accesses. And finally, our the test bench environment, so we can run that on the faster workstations so that it runs equally fast when we compare it with the Palladium. So apart from this, there are various other things we must think upon, like when we are writing the UVC code. Let's say we are writing assertions in our UVC based environment, we can move the assertions to the hardware so that they are synthesized along with the design. Then the overhead in synchronizing with each and every assertions for various events, that will be removed, and accordingly the test execution time will be safeguarded. And we must dump as and when required, rather than dumping the complete snapshot of the test case run. We can dump selectively, and once we dump selectively, and then we can debug faster and our test will finish sooner. So this is what I had with regard to this. So any questions? Hello? Hello?
Checking with the audience here if they have any questions.
Okay.
Yeah. Do you have any questions, Mr. Surinder? Surinder, I don't think we have any questions.
Okay. Thank you. Thanks a lot.
Okay.
Yeah.
Thank you very much.
Yeah. Bye.